screen? Can everyone hear me and see my screen?
We can hear you, but we don't see your screen yet.
You don't see my screen?
Not yet.
Not yet.
Okay.
Now.
All right. All right, that's cool. When can I start?
Yes,
or
yes,
can
now.
I start?
Now we can
Okay.
start.
So over this semester, I've been doing a project with my supervisor, Dr. Eric Howell at OSGRAB UWA on inferring the structured jet profiles of gamma ray bursts. And okay, hang on. Okay, yeah. So here are our goals. We explore the Bayesian inference using practical real-life problems, which is this very problem, which I will tell you, which is extending the code used in Howell et al. 2019 to infer the structured jet profile of GRB-170817A. And we'll be using the BILBI, which stands for Bayesian Inference Library, which is a package developed by OSGRAB in Monash University. So over here, we can see the signal for the multi-messenger event 170817. Down here where the cursor is, you see the nice chirp signal from the gravitational wave detectors. And over here, you see Fermi and integral signals, which are exactly 1.7 seconds after this. And what's unique about the 170817 event is the distance, which is the second closest GRB ever detected, and this is the closest GRB ever detected. And given this very peak flux, we see that the luminosity is of the order 10 power 47 ergs per second, which is very low because we thought that the luminosity cutoff would be around 10 to the 49 because that's how it has been in the past. We have not been able to detect anything lower than that in the past. However, this is at a relatively much closer distance, which is why it was probably detected. So in Gerardo's talk, we saw about top hat jets and structured jets. This is basically explaining what it is. Top hat is a constant emission Lorentz factor across the jet, and in the structured jet, we have the luminosity per solid angle decreasing like this smoothly outside the narrow core. We have two popular profiles, Paolo and the Gaussian. In this talk, I will only be exploring the Gaussian profile. So this is Howell et al. 2019. This paper is what my work is based on. And so this is how we infer the structured jet profile. So we assume a Gaussian jet profile with observationally motivated priors. Over there we have the luminosity, and we have the viewing angle and the core angle. So we choose our priors. The theta core, we have a uniform prior. The core luminosity, we can take a log normal distribution around the average short GRB luminosity is a prior. This is because most of our observations have been from high redshift, which means the top hat model works for them and we viewed them face on, so we can use those distribution. And the theta viewing angle is the Gaussian prior based on the radio observations, which we had in the Mooley et al. 2015. And it's around 15 to 25 degrees. And we have the likelihood, the log normal distribution over there. And these were the results. So we have our parameters over here and a nice corner plot over here. And we have over here the viewing angle versus luminosity, and the viewing angle versus peak flux. And the dashed line is the observed line, which shows us that our viewing angle was around 20 degrees. And we fold in this angular dependence into the Fermi detection efficiency, which we see over here. As we predict from our model, we get around 40 detections per year, which corresponds to the actual number of detections made by Fermi every year. So this is a good method of cross-checking. And yeah, so we have some interesting stuff about the 170817 in this graph of redshift versus minimum viewing angle according to the structured jet model. And over here, we see that our 170817 event was over here, which means it's right on the line. Had it been slightly further away at the same viewing angle, we would have missed it. And if it was closer, we would have been able to view it at a higher viewing angle. So we just managed to catch this gold mine of an event. And so what I also did in this project was I extended the model. So we have, I'm using observed flux instead of the luminosity function. And because of this, we need to include another parameter, the luminosity distance. We're using the same.
5 minutes.
Almost done. So this is the results that we got. We can see that the previous results are still the same, and we've managed to add another parameter to it. And these are other things that I looked to investigate, but was not quite so successful with because we lacked data. The first event was a solid gold kilonova. We had one data point. The second event, we didn't get good gravitational wave and electromagnetic data. And to conclude, this is my final slide. We inferred the structured jet profile. We've shown that this method can be used to make early predictions of the GRB light curve. Then I showed one way to extend the code using luminosity distance by using the flux. And we explored the Bayesian inference and found advantages. And I used the Bilby package developed by Osgrav in Monash University, and it has served me well. Thank you. That is my final slide.
Thank you, Roshan. Is there any question for Roshan?
Me?
Yes, Rosa.
Roshan, please could you tell us about your study about the gravitational wave counterpart of O3?
The gravitational wave counterpart of, I'm sorry, what? I didn't quite catch that.
In your previous slide.
Previous slide.
Here.
This one?
Gravitational wave.
Okay. So the 1904-25 event, is that what you're asking me?
What you did?
Yeah, so the 1904-25 event, there was only, Fermi could only observe 50% of the sky map, and to my knowledge, only one detector was running at that time. So we had a pretty large sky map, and CONUS is another instrument that gave us only upper limits, but we didn't really have much data to work on. So could not infer much about the structured jet profile here.
Okay, thank you.
Thank you.
Does anyone else have questions?
Any other question?
May I ask a question?
Yes, for sure.
Oh, sure.
Thanks. First of all, thanks for a talk. And also, can you go back to the corner plot that you showed on slide?
This one?
Right. Yes. Was this the first one that you showed? I think there were two.
No, the first one that I showed was this one.
Okay, exactly. So these are the posteriors for the luminosity in the core, the opening angle of the jet, and the viewing angle of 170817. Is that correct?
Yes, this is correct.
Okay, and so with respect to the priors that you put in, so the priors you put for the viewing angle were from Mooley, right?
Yeah, the radio observations. It was the Gaussian prior from the radio observations in Mooley et al.
Okay, and so from this corner plot, how much information do you have more with respect to what you put into the priors?
Well, we can see from...
Did the centers shift around, or?
I'm sorry, what?
Did the maximum values shift around, or did the uncertainty decrease, or? That's my question.
Well, from the corner plot, we get this nice graph over here, which shows us the degeneracy between the viewing angle and the core angle, and that was the most important piece of information that we were able to get from this graph. So when the core angle is wider, we have a wider viewing angle as well, and you can see that it was viewed at quite a wide angle over here.
Okay.
Okay.
That was the
Thanks.
most important piece. Yeah.
Thank you.
Thanks.
So I
Thank
think it's
you.
time for a break. Thank you, Roshan. I think it's time for a break now, if I follow the schedule. So we have a 15 minutes break for coffee or anything else. And we come back so at 47, 48 for well, people in France, and at 9:47 for the other ones. Okay?
Okay.
Okay, thanks.
Okay, so let's go to the break.